We are swimming in digital images, right? Selfies, memes, incredible photos. They're just everywhere. But have you ever wondered what they are? Like really? Today, we're going to peek under the hood. We are decoding the hidden DNA of every image on your screen to see what it's truly made of.
So, let's get right to it. That photo you just took? What's really there? It looks like a perfect little slice of reality, right? But if you could zoom in, like way in, what would you actually find? Well, it's not magic, I can tell you that. It's actually a pretty brilliant system of pure data.
For pretty much any photo that comes out of your phone or your camera, this is the answer. It's a bitmap image. The easiest way to think about it is like a giant, super detailed mosaic. It's a grid made up of thousands or even millions of tiny colored squares. We call them pixels, which is really just short for picture element.
And here's the thing about bitmaps that you've definitely seen before. You ever try to make a photo bigger and it just gets all blurry and chunky? That's called pixelation. You're not really making the image bigger, you're just stretching out those individual squares until you can see them, and poof, the illusion of a smooth picture just falls apart. But there's a totally different way to make an image. Enter the vector. Now, instead of a rigid grid of pixels, a vector is built from pure math. It's basically a recipe of instructions that tells the computer exactly how to draw lines, curves, and shapes using coordinates and geometry.
So when you put them side by side, the difference is huge. A bitmap is like a painting made of tiles. If you try to stretch it, the tiles just get bigger and look kind of clunky. A vector, though, is more like a blueprint. You can give that blueprint to a computer and say, hey, make this the size of a postage stamp, or make this the size of a billboard, and it will be perfectly crisp and sharp every single time. And that's exactly why photos are bitmaps, but company logos are almost always vectors.
Okay, let's circle back to our bitmap image for a second. Back to that huge grid of pixels. We know it's made of a bunch of colored squares, but how does the computer actually know which color to put in each square? How does it store the idea of red or that specific shade of blue?
Well, it all comes down to binary. You see, to a computer, every beautiful color you can imagine isn't really a color at all. It's just a number, a unique code made up of ones and zeros that acts as a very specific instruction. And that leads us right into this cool idea called color depth. Just think of it like the size of the crayon box the computer gets for each individual pixel. The more bits you use for a pixel, the more crayons you have to choose from. And more crayons, of course, means richer, more vibrant, more detailed images.
And check this out. Look at how quickly the number of colors just explodes. With just 1 bit, you get 2 choices, black or white. Simple. At 8-bit, you get 256 colors. You know that classic retro video game look? That's 8-bit. But when we jump to the modern standard, which is 24-bit,
the number of available colors skyrockets to over 16.7 million. That's what we call true color. It's a palette so huge that it actually contains more shades than the human eye can even tell apart. It's the secret to why modern digital photos look so incredibly real.
Okay, so let's just pause and think about this for a second. You've got a photo with millions of pixels, and each one of those pixels needs 24 bits of data just to describe its color. Well, the math gets out of hand really fast. You end up with these absolutely enormous file sizes. So how in the world are we sending photos back and forth in a split second, or storing thousands of them on our phones? The secret sauce is compression. It's this super clever process for shrinking down the file size, basically squeezing all those bits together to make the file smaller and way more manageable. And this is a big but. Not all compression is the same. Think of it this way. Lossless compression is like perfectly vacuum sealing your clothes for a trip. Everything's still in there, just packed tightly. You can open it up later and it's all exactly as it was. Lossy compression, on the other hand, is like packing in a hurry. You just decide, I don't really need all 3 pairs of socks, and you leave one behind to save space. Your bag is way lighter for sure, but you can never get that pair of socks back. So where do you actually see this stuff in the wild? Well, a JPEG uses that throw some stuff out lossy method. It's fantastic for photos because a tiny bit of data loss is pretty much invisible to our eyes, but getting that small file size is everything. PNGs, they're lossless. They keep all the data, which makes them perfect for logos and graphics where every single pixel has to be razor sharp. And then there are GIFs, which are also lossless, but they use that smaller 8-bit 256 color palette, which is why they're so great for those simple, blocky animations we all know and love.
And trust me, these technical details have huge, real-world consequences. That airline system couldn't handle a data overload. Think about the websites you visit. If a site uses giant, uncompressed PNG files for all its photos instead of smaller, optimized JPEGs, that page is going to load at a snail's pace. That drives people away, and it can cost businesses a ton of money. Choosing the right file type isn't just a nerdy tech choice. It's a critical decision that impacts everything.
So why should you care about any of this? Because understanding this fundamental code behind images and data, it's like having a superpower. If you're into game design, digital art, web development, or even something like cybersecurity, knowing how data is structured, stored, and squished down is one of the most essential skills you can have. It's what powers our entire digital world.
So the next time you snap a picture or share a meme or see a company logo, you'll know. You'll know exactly what's happening behind the curtain. The pixels, the vectors, the binary code, and the compression that makes it all possible. You know the code now. So the only question left is, how will that change the way you see your world?